We present NRDF, Neural Riemannian Distance Fields for learning articulated pose priors. Our goal is to learn data-driven priors modeling the space of plausible articulations, represented as the zero-level set of a neural field in a high-dimensional space. The learned priors can effectively model the pose of different articulated shapes. The learned priors can be applied to diverse downstream tasks such as pose denoising, pose generation, inverse kinematic from partial observations, and 3D pose estimation. However, existing works still encounter many problems. VAE-based methods like vPoser relies on a Gaussian assumption for the latent space. It has the tendency to predict poses closer to the mean of the Gaussian. Pose NDF alleviated this issue by learning a pose manifold. However, it faces challenges in accurately predicting distances for various levels of noisy poses. Existing work such as pose NDF still faces challenges. Firstly, there are no training samples near the manifold, which leads to inaccurate distance prediction. Additionally, existing work is based on gradient descent in Euclidean space, so it always needs reprojection after every projection step. It is always approaching the target pose on the manifold instead of reaching it directly. To address these problems, we first propose a new sampling algorithm, which draws more samples near the surface. Second, we propose an adaptive step Riemannian optimizer, which ensures the projection iterations always remain as valid articulated poses. The distribution of negative samples is important for learning a good distance field. However, pose NDF samples training poses by simply adding Euclidean noise sampled from Gaussian. It turns out there is no poses near the manifold. It causes the mean of resulting distance distribution far away from the zero-level set, which is contrary to the goal that the data should contain more samples close to the manifold. Additionally, simply corrupting data samples by Euclidean noise does not have explicit control over the distribution. Here we introduce our new sampling approach. Our goal is to perturb the clean pose and obtain the corresponding noisy samples. Firstly, we sample the geodesic distances from a specific distribution, and users can specify the distribution as they want. Then we sample directions from the tangent space of joint rotations, which is from the tangent space of k-articulated quaternions. Finally, we map the vector in tangent space to SO3 space by exponential map to obtain the final noisy pose. The new sampling strategy provides us the desired distribution. Our sampling approach allows explicit control over the resulting distance distribution. Consequently, we obtain more samples near the manifold, which is good for the training of distance fields. Using the novel sampling method, we create negative training samples which we use to learn our proposed NRDF. Considering a noisy pose theta k on the product manifold of Riemannian quaternions, our method aims to move it toward its nearest neighbor, ensuring it adheres to the Riemannian manifold. Specifically, the noisy pose should move along its tangent direction, with the step size which is the geodesic distance we aim to predict. During test time projection, the resulting pose at next step is obtained by taking the exponential map of the adaptive gradients. We define this process as RDF grad. The projection mechanism implies that our learning objective is to learn the geodesic distance for arbitrary poses, enabling us to obtain the gradient of the pose through network backpropagation. We first show comparisons between Euclidean and Riemannian-based projection. Compared with Euclidean projection, NRDF converges much faster while yielding plausible poses. We then evaluate our sampling strategy. Our new sampling results in more resonable converged poses than pose NDF. Now, we show the results of downstream applications. NRDF can be employed to solve inverse kinematics even with partial observations. Our method achieves better diversity compared to vPoser, while also preserving plausible poses. Here we show more results under different settings. NRDF can also serve as a prior term in optimization-based monocular 3D pose estimation. We show the initial prediction of simpler x on the left and our refined results on the right. Thank you for watching.